Hello and welcome to Through the Telescope, the podcast that puts the lens on astronomy. I'm Rose Waugh and I'm an astrophysicist and science communicator.
And I'm Elliott Bruce, and I'm neither of those things, but I'll be trying to find out why we should even care about astronomy. We'll be exploring some of the big topics in the field in little manageable pieces and have some fun along the way.
So, whether you know your red giants from your red shifts, or you're not quite sure what the difference between astronomy and astrology actually is, join us as we launch ourselves into the cosmos and try not to burn up on re-entry. Through the Telescope is sponsored by Pic Astro, the astronomy and astrophotography image sharing app, dedicated to your images of the cosmos no matter what stage you are on your journey around the universe. No ads, spam, or fake accounts. So this week we're talking about exoplanets again because we just haven't had enough of them yet.
Yeah, so last week we talked about the number of exoplanets, a little bit about the exoplanet formation to some extent, as well as some of the weirder exoplanets out there.
This time we're going to chat a bit about how we find exoplanets, and there are various different methods for that. So, yeah, let's start.
We've talked a bit about you having to find exoplanets with two different methods minimum. What are those methods? How do we go about trying to find an exoplanet?
Well, there are quite a few different methods, but the biggest method is the transit method.
Okay.
So that's found 3,941 confirmed exoplanets so far. So that's quite a lot.
A lot of them. Did you say 5,200?
Yeah. So that basically is planet passes in front of the star. It blocks out some light. This happens periodically. Happens every time the planet goes round. And, how that period occurs depends on the orbit of your planet.
Okay, so is that how... Because presumably if you also just had other stuff going in front of it, like another... a companion star or I guess a comet or something would probably be too small to see, would it? But, something else like a big asteroid blob. Mm-hmm. Do you know what I mean? Mm-hmm. Like they go round, but do they not go round so periodically? Or well, comets do, don't they?
So a comet would likely be far too small.
Okay.
I'm not sure what an asteroid blob is.
It's a technical term,
but you could have like a dusty disk or something.
A dusty disk.
Like a disk of material that's dusty.
Okay.
That is around your star, and it might be kind of clumpy or something, so that it doesn't block out any light, and then it comes around and it blocks out light.
Yeah, that's an asteroid blob, that is.
Okay, and that's what you mean by an asteroid blob.
I guess it is, yeah.
So, yeah, obviously if that is... That might look like a planet, right? Because it goes in front of the star, it blocks out some light, and then it comes back again in exactly however long.
Okay.
And then it comes back again in exactly the same amount of time. Because
it's like a year, the planetary year,
yes.
If that's the right word.
Yeah. You might be able to tell from what the dip in light looks like that it's not a planet. So it might be like really extended. And so you're going to be like, well, a planet's not that wide.
Right, yeah.
For example.
So you get a sort of a maximum size, or...
Mm-hmm. So you can literally think of it as you get like the star gives out a certain amount of light. You can plot what that light is on a graph. intensity on the y-axis and time on the x-axis. And you'll get a straight line that's, horizontal at some fixed value that tells you the intensity of the star.
Okay, yeah.
And then the planet goes in front of it, or the object goes in front of it, and there'll be a little dip at a particular time.
Okay.
And then, say it happens after a month. And then in another month, you get exactly the same dip.
You think something's going on here.
And then in another month, you get exactly the same dip. So, yeah, there's a pattern. But what that dip looks like might tell you it's probably not a planet, or it probably is a planet.
Okay.
Just because it's, it seems far too wide or whatever. But equally, it might not. So you might think you've got a planet, and actually you haven't.
Okay. So
you've got an asteroid blob, whatever that was meant to be, or stellar activity.
Oh, okay. It's like...
You might have some massive sunspots that are on the surface of the star. So the star goes round. There's a dip in light. It makes it look like there's something there. And then as the star comes round again, it reappears. And it happens periodically because the star is rotating periodically.
Right. But sunspots don't last that long, do they?
Well, some young stars are very active, and their active regions are quite different to on the sun.
Okay. But if you looked at it again in 50 years' time...
Yes, exactly. Then it probably wouldn't be there. Probably.
Does that mean people ever, sort of check up on these things? With the same method, but, ages later?
Potentially, yeah. Some stars do get a lot of... attention, and others less so. So, I think it depends. But from the transit dips, we can learn quite a lot. We can learn about the size of the orbit. So is it close into the star or far away? What's the size of the planet? Is it big or small? To be blocking out a lot of light?
So when you say the size of the orbit, is that based on how quickly it goes past?
Yeah. And you can also learn about the atmospheric composition of the planet as well.
Oh.
Because some light passes through the atmosphere, if it has one. And different chemicals have different signatures of light, so you can tell what kind of chemicals are in the atmosphere.
Chemicals.
So yeah, but the transit method, it's observed a lot of planets, but it does have issues.
It can give false positives.
It can give false positives, and it is a lot easier to see planets that are close into the star.
Okay.
So it's got a bias because you need the planet to pass in front of the star. So the further out your planet is, the lower the chance of that happening.
So would it be able to see...
It's just less likely to pass between you and the star.
Yeah. You've got to be there right at that moment in time because you're looking at this star and there's a straight line between you and the star, and if it passes very close to the surface of the star, you'll definitely see that. Whereas if there's sort of a Uranus type planet that's really quite far out, then it passes very briefly and only once every 13 years or something, so you've got to be, if not longer.
So it will pass a lot quicker and takes a long time to come back round, but also it's just, you're not necessarily looking into the plane where the planet is.
Oh.
So the planet could be orbiting that star in any inclination in comparison to the way that you're looking at it. So you might be looking into the plane where all the planets are.
Yeah.
Or you might be looking into the pole of the star and never see any planets.
Looking on top of, down on top of the thing. And you would never be able to see any planets.
Yeah.
With this method at least.
Yeah.
Wow, okay.
And the reality is you're somewhere in between those two extremes. So for planets that are far out, you've got much less chance of spotting them.
So, would you be able to see Mercury? Because Mercury is like really small, right? If you were an alien astronomer.
Yeah, maybe. I think it probably depends on how good your telescopes are. I'm not sure what the size limit is.
Okay.
Off the top of my head for the transit method. I'm sure it would come up with a quick Google though. So yeah, there will be at least from our current perspective and our capabilities, there's a limit placed on how small, in terms of size, not mass, your planet can be and still be visible, because it needs to block out enough light. So it's kind of like size relative to the size of the star, if that makes sense.
Is this also why, when they launch something like Hubble or JWST, that's like, oh, we're going to discover so much now because you've just, like, increased your resolution by 1,000-fold or something. So now all of a sudden you can see a Mercury or whatever. Is that the...
I mean, look at the differences between the Hubble images and JWST. You know, I mean, I think most of us have played with those little slidey bar images on various websites showing you Hubble on one side and JWST on the other, you know, and you kind of go like, you see what that exact bit of space looked like in the two telescopes.
I do love those slidey imagery things.
And, I mean, I absolutely love Hubble. Hubble has been our, I don't know, just like an awe-inspiring glimpse into the universe for all of our lives, right? But yeah, the resolution difference on JWST it's very, very noticeable, isn't it? Because decades of technology and engineering have progressed since then. So you're always going to get something better than what you had before. I mean, we will reach a resolution limit eventually, but it appears we've not reached it yet.
The other good thing about JWST is lots of hexagons, which is nice. I like hexagons and things. It's like a bee.
Yeah.
Whereas Hubble actually looks like a telescope in space.
Yeah.
Which is pretty cool. I think I prefer the look of Hubble to the look of JWST. That might be controversial.
I think it is controversial, but...
It might be in a sense of nostalgia, though.
But I was going to say, for me, I definitely agree. There's like a definite like nostalgia and comfort and, I don't know, thing associated with Hubble. Yeah.
Also, I've played a lot of Sid Meier's Civilization games, and in at least, was it Civ 4 or was it Civ 5, you could actually launch the Hubble Space Telescope.
Really?
So, yeah. I think it gave you some free great scientists or something and meant that you were better at a space race, which then meant that you would go to Alpha Centauri or something? I'm not
Going to be a
sure.
long time before that happens.
Well, it's the end of the game at that point, so...
Another method that you might have heard of, it's also found quite a lot, but substantially less, at 1023. Radial velocity method. That's watching for the wobble, it's sometimes called.
The wobble.
Yeah.
I already like the sound of this one.
So the planet orbits the star. The star and the planet both have gravity.
Yeah.
And they influence each other. So the star makes the planet go round it. You know, the gravity of the star causes the planet to orbit it. If you want to be a bit more sophisticated. But the gravitational effects of the planet on the star also exist. And so the star also moves under the planet's gravity.
Right, okay.
But it doesn't, it doesn't...
it doesn't orbit.
It doesn't, exactly. It doesn't orbit it. It just wobbles.
Yeah.
It might do like a mini circle or a mini ellipse. Or it might just wobble. It might move so slightly that the star doesn't actually move in space, if you see what I mean.
Yeah.
It kind of just like wobbles about its own orbit, kind of.
Yeah.
And this movement can be seen in the star's light through Doppler shift. So, light can be described as a wave.
Or a particle.
But right now we're describing it as a wave. If an object is moving, then the shape of the wave gets stretched or squished, right?
Yep.
So the movement of the star pushes the peaks of the wave closer together, or it stretches them further apart. And this changes the frequency or wavelength of your light. Therefore, it changes the colour of the light.
Yeah.
So the colours of stars can be seen to change as the star goes about this little wobble or orbit that it does.
Okay. Okay, so it's like a little colour change, a sort of colour oscillation.
Yeah, exactly. It's an oscillation. So as it moves away from us, it gets redder.
And then as it moves towards us, it gets
It
bluer.
gets bluer. But it kind of stays about its actual colour.
Yeah.
It just oscillates a bit.
The wavelength gets slightly shorter, slightly longer.
Yeah.
Then you can do some nice plots of that, and then some clever people put it into a computer, and they work out that there's a planet there that's like a certain mass.
Yeah.
That is at a certain distance, or is it like it's this mass ratio, like, you know what I mean?
Yeah,
like
I imagine it's linked.
a distribution of masses and radii that fit that equation or something.
But earlier when we talked about minimum and maximum masses or whatever it was that you asked.
Yeah.
So that's the issue that the radial velocity method has, is that it can estimate a minimum mass, but it can't accurately determine the mass of the planet.
Right, because it could be like, it's, let's say, infinitely far away and infinitely massive, and it would have the same impact on its wobble as something quite close that's relatively small. Got you.
Yeah.
Got you. That's a fair few exoplanets, 1,023. So that's not to be sniffed at. No.
The next biggest one, quite a step down, 152.
Okay, well, I mean, I've not discovered any, so 152 is pretty good going.
So that's gravitational microlensing.
Okay. Sounds like black holes.
Pretty trendy, so a lot of people have probably heard of this one. So gravitational lensing happens when a massive object passes in front of another massive object.
Okay.
And the gravitational well of the closest object causes the light from the behind object to be bent or focused towards us.
Right, and this is Einstein talking.
So if a star passes in front of another massive object, this causes it to get brighter.
Right.
Or a peak in the light data.
Okay.
Microlensing is the same thing, but on a smaller scale. So it's been used to find planets. If you have a star with a planet around it, and this passes in front of something else, like another star, then the peak from the star that's lensed can be seen. But also there's like a secondary peak that's smaller.
So you've got to have
that's
two
caused
stars.
by the planet.
You've got to have two stars, do you? And a planet.
Yeah,
and
one thing has to be far behind, the other thing has to be in front.
So is this like a binary system? No, this is two completely different systems that happen to be like perfectly aligned.
From our perspective.
Yeah. Well, I can start to see why there's only 152, I guess. That seems like you're starting to ask for quite a lot of...
I mean, the star isn't always, from our perspective, behind this other star.
Okay.
Because when you think about it, as the Earth rotates and as we move through space as well...
there's a bit of a slight variation in terms of where we are, where the stars are. But...
Yeah.
Jeez. That one sounds complicated and very I was going to say very clever, but the other one's very clever too. It's just that this one sounds like a sort of complicated theory.
Yeah, it's got theory and it's also got Einstein associated with it, so people are scared off, and it also makes it sound super clever.
It's highfalutin.
Mm-hmm.
That's what it is.
Well, you'll like the next one then.
Okay.
The next one is not that.
Okay. I think I probably...
Direct imaging.
You take a picture of it.
Take a photo of
Okay.
your exoplanet.
Okay. How close does it need to be for me to take a photo of it? Because in the previous episode,
pretty
we
close.
said that we couldn't necessarily see Uranus or Neptune that easily.
Mm-hmm.
So
direct imaging has found 62 exoplanets. So maybe more than you might have thought.
that's... Yeah. So we've got 62... Is this confirmed or is this...
Confirmed.
Okay, so we've got 62 pictures of definite exoplanets.
And it's very difficult, like you said. It's very difficult to do. But it doesn't necessarily have to be visible light.
Oh, okay. It's still impressive, but
So,
we're starting to...
because you could do it with infrared.
Mm-hmm.
That's the same thing. It's just that your eyes can't pick up on it.
Yeah.
But you do it with infrared, and then you make a picture just exactly like a photograph from visible light, but at a different wavelength. And the computer just changes the colours on your photograph to a thing that you can see.
Yeah.
So, yeah, it's pretty difficult because the star's glare usually makes it pretty much impossible
Jeez.
to do.
I'm also guessing
It's
that
good for seeing planets that are pretty far out from the star in that sense. Because the star isn't, out-glaring them.
Yeah. I'm assuming
But it's
that we're not...
completely useless for anything that's really far away from us. Or for very bright stars.
So it needs to be a planet that... Or it's better for a planet that is quite far away from its star. But the star can't be really far away from us, otherwise we won't be able to see it. I mean, that's impressive that we've got a picture. I assume it's just sort of like there's a white splodge. Well, not necessarily white, but, there's a bright instead of white.
Well, there's one...
Dot-ish.
It typically, I think, is not that good for multi-planet systems. But I'm pretty sure there's one paper where they've got 4 exoplanets. And they've got a picture of the star with 4 exoplanets. I think that was using infrared.
Gee, I mean, that's insane that
Yeah.
we've got pictures of planets in another solar system. Sorry, we're calling it stellar. What did you want to call it?
But whatever you want.
I'm going to say solar system.
Yeah.
Jeez.
Wild, isn't it?
That's so wild.
Another method, which is kind of similar to radial velocity, is called astrometry.
The radial velocity is the wobble one.
The wobble, yeah. Astrometry's only found 2 so far.
Okay, that one's pretty poor. That's only 2 more than I've found. So
you're looking for tiny movements of the star that's caused by the exoplanets.
Okay, so I can see why that one's similar to the wobble one.
Yeah. So what you're doing is you're looking at stars in the night sky. Stars move in the night sky. You've probably noticed.
Yes.
Planets influence the motion of their host stars through their gravity, which we talked about. And these movements are really small, right?
Mm-hmm.
But if you're watching the stars and tracking them, you might notice that it's moved a bit.
That must be so finicky.
It's insane,
You
isn't
must
it?
have to...
Imagine the precision that you must need to do that.
Is that sort of for finding something the size of Jupiter, say? Because, presumably, the Earth isn't really doing that much to the sun.
Mm-hmm.
To be able to just sort of measure a star where it is relative to other stars, presumably, that just seems insane. The uncertainties in that must be astronomical. That was too cheesy. But that, jeez. Well, they're all Very
all
different
impressive.
and all very impressive methods,
Yeah.
to be honest. Have you found any Earths out there?
Not exactly the same, but Earth's similar-sized planets, yeah. Rocky Earth-sized planets, yeah. So, I mean, it depends what you're asking, really.
Yeah, I mean, I guess, what is an Earth planet? Because I imagine if you were looking from outside our solar system, if you saw Venus, you might be like, yeah, that's probably an Earth planet, or maybe Mars. I guess Mars doesn't have an atmosphere, so that would help. But
Yeah, so I think if you were looking from outside the solar system, Mars would be noticeably different. Doesn't have an atmosphere. Venus would be noticeably different because whilst it maybe might seem like the right size, its atmosphere is wrong. Very, very different to Earth's atmosphere. Yeah. As we're learning by asking questions about what makes an exoplanet habitable, defining what makes Earth is quite difficult,
Yeah.
because there's a lot to consider: the size, the composition, its atmosphere, exactly where it is around the star, the exact type of star that it is. It's a very specific. There are quite a lot of parameters that you're trying to meet, and you can rack up more even quicker depending on what it is you're trying to ask, really. So it might be quite easy to find a planet that's similar in size to the Earth, and then it's likely to be made of rocks if it's that size. It's probably not going to be a gas planet at the mass of the Earth. And then is it exactly kind of the right size as well as mass? Therefore, it's made of the right kind of rock.
Right, yeah.
And is it around the right type of star? And how old is the star?
Yeah.
Is it like the sun, or is it in a completely different part of its life cycle? And then exactly where around, what's its orbit like? If the star is exactly the same as the sun, then presumably you're looking for an Earth that is, 1 AU, 1 astronomical unit.
1 Earth distance
One
from the
Earth
sun.
distance from that star. But if the star is cooler than the sun, then you're going to want to put your Earth less than that. You're going to want it to be closer. Otherwise, you won't have liquid
you'd want
water.
it to be a bit further away. This is like the Goldilocks zone kind of idea.
So, yeah.
Because so to some extent, so when people have talked about exoplanets, planets out there, first thing that pops into my head is, when are we going? Because that's what happens in movies, right? Then the next thing that happens is, we're never going because it's like a bazillion trillion miles away and it would take us 40,000 years to travel there at the speed of light or something. But I feel like it's always in the news of when they talk about exoplanets, like almost as if, yeah, we would totally go there, or like we could go there. There's an artist's depiction of this planet, which looks like
based
this,
off
and
like a few things that the scientists have said about the planet.
yeah, and like, are people looking for planets that look like they could be an Earth or a home for life for us or for other people that would have evolved? Is that kind of the thing?
It's a very philosophical question. I think that humans intrinsically, we want to understand ourselves and our place in the universe. And I think that people therefore have a few different reasons for maybe looking for Earth-like planets around other stars, but they all come down to the same kind of thing, really, of trying to understand ourselves. And maybe that is, you're looking for somewhere that could host life similar to us. Maybe you want to know that we're not the only life out there. Or maybe you believe that there's more life out there, and so you're trying to show that. Or maybe you're wondering if we are the only life out there. If you know what I mean, like the opposite side of that coin.
Yeah.
Maybe you're trying to understand what the Earth was like when it was younger. How did it come to be like it is now? How likely was that? Was that bound to happen? Or was it just like super lucky that like we met the right criteria and we managed to sustain that, and maybe that was unlikely to happen, that we would get to this point, or not. Maybe it was very likely once you had already met a few conditions early on at the beginning of the solar system. So I think there are a whole bunch of reasons why people might be interested in finding planets like Earth, and why it appeals to the public and to the news and just humans in general. But they all kind of come down to the same thing of trying to understand ourselves, I think, don't they?
Right, so even if you're looking at, like, Jupiter-like planets, then you're sort of trying to understand the solar system and the sort of thing, sort of the science behind solar system formation in general, and therefore, like, why our Jupiter looks like the way that our Jupiter looks like. And if you're looking at more sort of rocky planets, then maybe you're thinking, why is it that these planets are here and not out there, or whatever, and maybe that's how the Earth and Mars, etc., formed.
Yeah, I think a lot of scientists, a lot of astronomers, that's not what they think day to day.
Yeah.
What they think day to day is that planet is so interesting. Why is it like this? Why does it have this in its atmosphere? Why doesn't it have this? That's very puzzling. It's like you're stuck in that like nitty gritty of like looking at the details. Do you know what I mean? But when you take a step to think, why does this actually interest me? And you ask why a few times to get to the bottom of what it actually is. I don't know. A lot of astronomers will, we're all human. And I think it is a curiosity that we have. I think it's a curiosity that a lot of humans have. We all have it in different ways. And we apply it to different things, Some people are very interested in where the universe came from.
Yeah.
I am not. I really am not interested in the Big Bang or anything like that. Like, I'm glad someone's researching it, but I'm really not that interested. And I can't really think about it or hold a conversation on it for that long. But I think it's the same kind of question,
I think the answer a lot of the time is just people think it's cool and they're doing some fun stuff that's cool, which is not necessarily the same as we're learning about the solar system or whatever. We're learning about ourselves, It's just like we're having fun. Do you know what I mean?
Yeah, I think it is that, but why is it fun?
Because it's really far away and you can look at it and work out stuff about it. And nobody's ever going to go there. And that's amazing. You just found out stuff.
But why is it amazing?
Oh, why is anything amazing?
I feel like a lot of the human experience is trying to understand our place in the universe.
Fair.
Ultimately. But we're so like high thinking, that we don't always recognize it as that, I think.
So we've spent quite a lot of time in this episode and the previous episode talking about exoplanets. But what I was thinking, bro, is actually that we know a lot of exoplanets in popular culture.
Yes. It really captures the imagination of people, doesn't it? Scientists and artists, if that's the right word, alike. Yeah, lots of cool exoplanets in, literature or TV movies.
Yeah, I think the thing that comes to mind for me, first of all, is the sort of TV and movie versions. So, like, you got your Star Treks and your Star Wars. I mean, literally every episode, not quite every episode, but almost every episode of Star Trek is a completely different exoplanet.
Yes. Yes, to some extent.
Yeah, okay.
It's a different exoplanet, but
a lot of the time, the type of planet doesn't really matter that much. It's just like, this is kind of like Earth, but it's Proxima Nebula C or something.
Or it's, like a sand planet.
Yes.
Or a water planet.
I feel like that's...
and the entire planet is sand or water.
Like Dune.
Yes.
In fact, I think, so I've read Dune, and I have opinions on Dune, which I don't think are necessarily particularly popular. But I appreciate that Dune exists, and I know that things came from Dune, and the guy that wrote it put a lot of work into it, and there's like a lot of science behind it and ecology, blah, 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 blah. But I'm pretty sure, so the main family that the whole thing starts off, they're based on a water planet, I think, to start with.
Right.
At the very beginning. And they're getting moved to be in charge of Dune. Arrakis? Is that what it's called? The desert planet.
I don't know. I'm taking your word for it because I'm going to be honest. It's a bit, shameful to admit, but I haven't actually read Dune. So I started reading it, and I got however far through, and I just was like, nope, I cannot finish this. It's massive, and I just wasn't enjoying it.
Yeah, that's fair.
For many reasons, but we're not gonna go into that.
No.
But the point is, you are the Dune expert here, the two of us. So.
Which is saying something. I've only read the first one. I have heard from people that do really like Dune, that the other books are not good. But you might disagree, dear listener. But yeah, I feel like the sameness is also true in Star Wars. I mean,
yes.
they say that Dune is like the
Hugely.
inspiration for Tatooine, or inspiration / direct lifting.
Mm-hmm.
They didn't have sandworms in Tatooine, but or do they in the Sarlacc pits? Is that what it's called?
Yeah.
That's a prequel, so is it?
Oh dear.
Anyway, the point
is the planets are all the same, and how realistic is that? I think it is interesting, isn't it? Because we kind of look to other planets, especially in the solar system, where we feel like we know them quite well, which I would say is probably not true. And we kind of paint this picture of them being samey. Mm-hmm. Mars is the red sandy planet. Mm-hmm. And we just neglect everything else about it. We don't even really mention the polar caps a lot of the time.
Which are substantially different, right?
Substantially different from red sand. And I think the same can be said for a lot of the planets. And it's probably partly because we don't know very much about them, but we just we do make them quite one-dimensional.
Yeah, I wonder if that's also an element of sort of education, as it were. When NASA or whoever is telling the public about this is what the planet is, then it's easier for people like myself to be like, oh, yeah, Venus has got a toxic atmosphere. Whatever. It's just that's all you need to know. It's just one sort of big green toxic cloud.
I guess, but I guess it's also, I think it is also, we just don't know enough about them a lot of the time to say all that much. But yeah, some planets presumably are quite samey.
Yeah.
I'm not poo-pooing that idea.
Yeah.
It's just, Star Wars, Star Trek, other things. They can be very one-dimensional exoplanets, can't they, in science fiction, at least in those cases.
Yeah, I quite like...
Which is especially irritating to me. That's fine if it's a barren planet. No problem with that. Fine. It's a planet that's just sandy. Okay. But as soon as you start making it like a planet that has various life forms on it,
Yeah.
I cannot get on board with that. It cannot be so one-dimensional and support so many different species. It's like there is no ecosystem there. That's not how ecosystems work. That just doesn't make sense.
Yeah, it's kind of like poor sort of world building, as it were. It makes me think of... So I really like... I've not finished. I've read the first two now. Of the Broken Earth trilogy by N.K. Jemisin, who... I think she was the first person to get 3 Hugo Awards in a row for 3 books in the same trilogy.
Wow.
Which is something to put on your wall as well as your CV.
That's insane, yeah.
So it is, I think she says in the end of the first one that she went to like a sort of NASA creative writing course or something like that. It was like NASA invited, I think, a bunch of people to come on down to wherever. And their point of view was people learn about science from popular culture, so we should get popular culture people like authors, etc., to learn about science so that then they can write something that is like correct, kind of thing. And so the Broken Earth trilogy is very sort of geology based in a way. There's lots of like sort of tectonic plates and stuff, and it's sort of it is a dystopian sort of it's an arid planet, but there are like there's variations in sort of coastal and polar geographies or biomes, and it's just cracking, really. But
is that partly because it feels realistic? It makes it feel more real.
Yeah, I think so. I think it's
as well as the fact that she's, clearly an amazing author.
Yeah, so I think as well as it is not just the sort of the geography and the sort of geology, the earth science, as it were. It's also the interaction between that and the people, as it were. So there's like a sort of strong sort of link between sort of all the aspects of the setting and the characters and the plot and everything. So
just generally 10 out of 10.
It's just generally 10 out of 10, I would say.
Yeah.
So, yeah, it's kind of another author that I've not read enough of is Ursula K. Le Guin, famous for
very famous
Earthsea trilogy, also which I've not read, and The Left Hand of Darkness, which I really enjoyed. And in that one, I think it's meant to be a bit like Earth, but a little bit further away from its star, or its star's a little bit weaker, so it's sort of a colder planet. So there's a lot of it. It's not quite just a winter planet. There are seasons and there's variations, and again the environment plays a big role in the story.
Yeah, it is interesting, isn't it? The connection between science and literature, especially with astronomy. There's a lot of like sci-fi, and that's very within popular culture, and a lot of us grow up reading it and immersed in it before we even become scientists. And so there's a lot of interplay that goes on between the two, really, where science informs sci-fi writers of new, more realistic, perhaps, ideas, and the sci-fi authors, can come up with some crazy left field things that maybe go against science at the time, but later have shown to be maybe not quite so crazy
Yeah.
as when they, dreamed it up. But also it feeds into the next generation and the scientists that grow up reading all of that literature or watching all the movies, TV, whatever. That's becomes a part of their identity and their experience of the world and their understanding of the universe, even when we know it's fictional. It kind of normalizes some things, perhaps. And how much does that then influence your work as a scientist, what you find believable or not believable?
Yeah.
When you are looking at your data. Yeah, it's quite interesting.
And
speaking of that, it's not as if exoplanets are, exclusively in kind of more grown-up sci-fi. It really has taken hold as a thing in popular culture, because kids' stuff is absolutely riddled with it as well. Mm-hmm. Even from quite long ago. I mean, the Clangers.
That is an exoplanet.
On BBC.
Well, they do pan across from the Earth to the blue planet.
It zooms, though.
That's true.
It definitely goes past different stars. It's definitely an exoplanet. But, we grew up with that. They've now remade it in actually a better way.
We didn't grow up with it when it first aired.
No, we're not that old. But that's also, I guess, where I'm going with that. It's pretty old, really.
Yeah.
It's very well established within British kind of kids' culture. If that's the right word.
It's it's from the same kind of time as Bagpuss, isn't it? Originally.
Also cracking, but not got exoplanets in it.
No exoplanets, technically, no. And they've not made a remake of that one so far. I don't think,
no.
So. And also, you used to watch Astro Farm.
I did.
Which I vaguely remember. And Molly's Gang, which is
Molly's
just aliens
Gang.
on a planet.
Recently got that DVD for our wee one.
Yeah.
Thankfully, they're as mad about it as I was, so that's good.
But yeah, I think as a kid, the sort of two major things you're excited about are planets and space and dinosaurs.
Yeah.
And like you were saying, dinosaurs clearly don't have feathers, because none of them do when you're a kid.
Yeah.
And I've seen Jurassic Park, they don't have feathers. And turns out scientists say some of them have feathers.
Which is still maybe not that weird an idea.
No.
Considering what has evolved from dinosaurs.
Turns out birds also have feathers. But
breaking news.
Are there any that don't? I mean, even
penguins I think it's a
things.
requirement, isn't it?
Might be.
Don't know what the actual word is.
But then a platypus is a mammal, and it lays eggs.
Yeah, well, so I'm thinking of, sorry to add more kids' TV to this, I was thinking of storybots.
Oh, yeah.
I feel like they say that one of the things that you need to be a bird is to have feathers, and storybots are not, they're not shy about giving counterpoints to things. I don't know. Well, maybe one of our listeners knows, do birds have to have feathers?
Maybe.
But yeah, so exoplanets and sci-fi are very common.
Yeah.
There's a lot more we could say about this, but I think perhaps this might be where we should leave it.
But if you want to tell us any of your favourite exoplanets, you could let us know. Any that we obviously missed out. I mean,
any really good books or movies or TV shows at us on social media, and let us know.
So that just about wraps things up for this episode. Please, can we encourage you to subscribe to Through the Telescope wherever you find your podcasts, and if you like, you can leave us a nice positive review as well. It really helps the show, and it makes it easier for more people to find us.
Feel free to send us any comments, questions, or suggestions of things or people you'd like to hear about or from in future episodes. Or perhaps to put yourself forward to chat about your own astro research or experiences. As always, you can find us on Instagram at Through the Telescope Podcast, or you can find me at astrophysicist_Rose. You can also find us on Twitter at The Telescope Pod, and you can contact us by email at throughthetelescopepodcast@gmail.com.
And with that, we'd like to thank you very much for listening, and we look forward to seeing you again next time.
Bye.
Bye.